Welcome to the fourth and final video on buckling. In this one, we'll go through a quick example looking at a column of a fixed length, but we'll look at different boundary conditions it can have and how that will affect the buckling stress. Let's say we have an HSS column, 4 inches by 4 inches, that is 8 feet long and has the normal Young's modulus theory. Let's think about all of the different boundary conditions it could have and work through those. So the first one, obviously, is pinned. For that, we're fortunate the constant that we multiply that by to get the effective length, right? So we're gonna say that K times L is the effective length. K is 1 for pinned because it's the assumption we made at the very beginning. So that means that the effective length is equal to 1 times 8 feet, which I'm just going to go ahead and call 96 inches. And then we're going to want to use our equation for the critical stress. Let's look at the critical stress. And that's going to be equal to pi squared times the Young's modulus times the radius of gyration squared divided by the length squared. And in our case, that's going to be, and that's effective length, pi squared 29,000 KSI. The radius is 1.5. And that's going to give us 6, 4, 3, 9, 1.7 over the effective length squared, and that's going to be kips. Throw a comma in there too. So for pinned, our effective length is equal to 96 inches. This becomes 69.9 KSI. Now let's look at a fixed. So fixed on both ends. For this one, for a fixed, let's box all these as we go. For a fixed, K is going to be equal to 1/2. So in that case, our effective length is actually only going to be 1/2 of 96. It's going to be 48 inches. When we plug that in, we get that the critical stress, if it's fixed, is going to be, 643 991.7 over 48 inches squared. And that's going to give us 279.5 KSI. Again, let's box that. If we have a fixed free, K is going to be equal to 2. So the effective length will be twice 96 inches, or twice 8 feet. That's going to be 192 inches. That's going to mean that our critical stress, 64391.7 192 inches squared, and that's going to give us 17.5 KSI. Not so much compared to that second one where it's fixed. And finally, let's look at a fixed pinned, which I don't believe I went over before, but a fixed pinned is going to have a K value of 0.7. It'll be a little bit more effective than a pinned. So we're going to end up with that same top bit. Turns out that pi squared Young's modulus radius squared doesn't change. 991.7 kips divided by our length. Oh, I didn't write our length. Our effective length, 0.7 times 96 inches is going to be 67.2 inches. We will, of course, be squaring that down there, and we end up with, for this one, 142.6 KSI. Now, the material that most HSS rectangles are made of is going to have a yield stress of about 46 KSI, or at least that'll be the minimum. So what that means is that for most of these, it's going to yield before it reaches the buckling stress. It won't have a chance to buckle if it's pinned, or it's fixed for sure, or even if it's fixed pinned. But if it's fixed free, it'll buckle well earlier. Right? It'll buckle at only 17.5 KSI. So there's a really wide variance, right, as far as how what the buckling stress is for this same cross section, same material, just different boundary conditions. So that was a good time, right? These obviously will not govern. 8 feet isn't very long, but so it'll crush first if it's only 8 feet long and it's fixed on both ends, or it's pinned on both ends. But if we've got it fixed free, or then it's going to be not, or there's really nothing else other than a fixed free that this would be at, but we see we've got a very low buckling stress. And then, of course, fixed is going to be massive. Right? That's more than 10 times as great as a fixed free. So, pretty cool.